to BE square plus EM square. BM square is BE square is again capital D square plus EM square is, this is x from O to M x, this is d by 2. So, x plus d by 2 the whole square. Now, BM square minus AM square is d square plus x plus d by 2 the whole square minus of AM square is d square plus x minus d by 2 the whole square. Or we can write BM square minus AM square is d square plus x square d square by 4, 2xd by 2. So, I am writing as xd minus of d square plus x square plus d square by 4 minus 2xd by 2, that I am writing as xd. This is plus d square minus d square plus x square minus x square plus d square by 4 minus d square by 4. So, you have BM square minus of AM square is minus of minus xd plus xd. So, this is 2xd. This BM square minus AM square you can write BM minus AM into BM plus AM is equal to 2xd. Here, since practically all the points, this M point will be lying very close, this BM and AM approximately we can take as D. So, this will be of 2D, BM minus AM, which is equal to 2xd by 2d. So, this BM minus AM is nothing but it is the path difference. So, this path difference is equal to xd by d. Depending on the path difference condition, this point M on the screen can be a maximum intensity point or it can be a minimum intensity point. Now, we have derived the expression for the path difference x small d by capital D. The condition for the bright fringe, that is on the screen, if the point M, if it has to be a maximum intensity, then this path difference must satisfy the condition n lambda, or we can say x is equal to n lambda d by d, where we know this x is the distance from the point O, where n is equal to 0 plus or minus 1 plus or minus 2 etc. If n is equal to 1, x1 is equal to lambda d by d. If n is equal to 2, x2 is equal to 2 lambda d by d. If n is equal to 1, x1 is equal to lambda d by d. It means this x1 is the distance of the first bright fringe from the point O, and this x2 is the distance of the second bright fringe from the point O. Now, the distance between these two bright fringes x2 minus x1 is equal to 2 lambda d by d minus of lambda d by d, which is equal to lambda d by d, the distance between the two consecutive bright fringes. Now, the point M if it is a minimum intensity point, then it should, the path difference should satisfy the condition 2n plus 1 lambda by 2, or the distance x where this point m will be the minimum intensity point is x is equal to 2n plus 1 lambda d by 2. Again n is equal to 0 plus or minus 1 plus or minus 2. If x is equal, n is equal to 1, x1 is equal to 3 lambda d by 2. This x1 is the distance of the dark fringe from the point O. If n is equal to 2, x2 is equal to 5 lambda d by 2. This x2 is the distance of the minimum intensity fringe, that is the dark fringe from the point O. Now the distance between two consecutive dark fringe x2 minus x1 is 5 lambda d by 2 minus of 3 lambda d by 2, which is x2 minus x1 is equal to 2 lambda d by 2 lambda d by, sorry, x is equal to 2n plus 1 lambda d by 2d, here 2d, 2d. So now this is 2 lambda d by 2d, which is equal to lambda d by d. So now we can see that the distance between two consecutive bright fringe is lambda d by d, and again the distance between two consecutive dark fringes lambda d by d. This is called the fringe width. The fringe width beta is lambda d by d. So if the wavelength of the source of the light is known and capital D is the distance between the sources and the screen, and small d is the distance between the sources, we can calculate the fringe width beta. Now we will see the next phenomenon of light, diffraction. This diffraction is nothing but bending of the waves. This diffraction phenomenon is easily observable in sound waves. Say for example, if I am taking the class here, the students, those who are standing outside the class, can hear my voice. This is due to the diffraction of the sound waves. Sound waves easily can bend around the corners. Since the light also is a wave, this diffraction phenomena definitely is expected in the light waves also. So what is diffraction? Diffraction is nothing but the bending of the light waves around the corners of an obstacle. This S is the monochromatic source. The light rays coming from this monochromatic source, we expect that in the screen it should illuminate the portion from the point P and Q. Thus it travels in the straight line, and the point P and Q, up to this only we expect the intensity. Whereas actually what happens, we see some intensity which goes on decreasing on both the sides of P and Q. This is due to the wave nature of light, that is the bending of light rays which enters in the geometrically prohibited region also. Now we will see the difference between interference and diffraction. In interference, this is the central maxima, first order maxima, second order maxima, on both the sides will be there. All the maximum intensity will be, bright fringes will be having the same intensity, and all the dark fringes will be having the same intensity, that is the minimum intensity. Whereas in diffraction, the central fringe will be of the maximum intensity, the brighter one, whereas the first order maximum, second order maximum, the third order maximum, even though they are the bright fringes, but the intensity goes on decreasing. The second difference between interference and diffraction is, in interference the fringe width, as we derived lambda capital D by D, fringe width of all the fringes remains the same, but in diffraction the fringe width beta does not remain the same. Here in interference, conditions for maximum intensity is n lambda and condition for minimum intensity is 2n plus 1 lambda by 2, whereas in diffraction the conditions for secondary maxima is 2n plus 1 lambda by 2 and the condition for secondary minima is n lambda. Here n is equal to 0, 1, 2 etc., whereas here n is equal to 1, 2 etc., where the intensity of the central maxima is maximum, I have marked as I maximum, where the path difference is 0. Now this completes the wave optics. Thank you.